Well, welcome back. We are in the subject of registers and counters. We started this last time. We defined a register to be a sequential logic circuit which deals with the storage and transfer of multi-bit data. We found out that we could transfer data into these registers four different ways. And the types of registers that we looked at included the following. Now, pay attention to these mnemonics as I'm going to bring them out here in a few minutes, momentarily. The data latch register, which performs parallel in, parallel out, primarily data transfers. So here's showing 4D flip-flops. Data coming in parallel, I hit the clock, and that is registered then on the outputs. Typically, we use D flip-flops for this. The shift register, on the other hand, works primarily with SISO, or serial in, serial out data transfers. I can build a shift register two different ways. I can build it with D flip-flops. Every time I hit the clock, it moves one bit at a time across. Or I could use JK flip-flops, which are configured to act like D flip-flops, and they do the same thing. Now, beyond that, we can actually have variations of data transfer, such as serial in, bring it in serial, and take it out in parallel. In fact, that's how the internet works. You receive internet signals wirelessly in serial form, and then they are packaged in parallel form to enter your computer and be processed. We also covered a couple examples showing basic operations of a shift register, and I will refer you to last time to look at that, and you can review this. On a exam, I would be expecting you to handle these kind of problems. Now, the last thing about the shift register that we got into was the example of having just two flip-flops and entering data on this side and then shifting them across. Actually, we shifted them the opposite direction, as we'll now show. So here's an exercise that we did on an iClicker. We have two JK flip-flops. The data is now being manipulated such that it moves from the left to the right. And we are set them up a little bit differently. In this particular case, we crisscrossed the output to the K, and then the not Q went to the J. What we did here is we looked at, let me turn off the iClicker exercise here just for temporarily. That'll be fine, I guess. What we looked at is applying two clock pulses to these two JK flip-flops. And since they're negative edge triggered, we expect them to change on the negative edges as shown by these dotted green lines. The first flip-flop was configured into toggle mode, so therefore this chart is for toggle. For the first flip-flop, toggle once here, toggle a second time here corresponding to second flip-flop. The data came in as a 0, it toggled to a 1, and then came out as a 0 after two toggles. In the second flip-flop, we initially set the second flip-flop. Now remember, they're crisscrossed, so in this particular case, K would be a 1 and J would be a 0, although it shows 0, 1 here, but that's because they're being crisscrossed, so don't be confused by that. So the data was set here, indicating that I have a 1 on Q2, which is this flip-flop here. And then as the first flip-flop changed its state due to the change that the first flip-flop endured, then it became a reset operation, and the final answer was a 0. Now, I promised you to give you another example of this to work out on an iClicker exercise. In this particular case, I made it a little bit easier. I just straightened out the line so the Q is going directly to the K. We're going to, again, assume initial conditions of the first flip-flop being a 0, as it was here, and the second flip-flop being a 1, as it was here. Now, we are going to change the problem, though the input is going to be a set condition here, and the input to the second flip-flop is going to be a reset condition. Now notice this reset here and this reset are the opposite because of the crisscrossing of the lines. So what I'd like you to do now is to complete the 4 values that should be in this table in a similar manner that you saw over here. I'll give you a hint on this, that this set and this reset applies. The set applies to the first flip-flop here, and the reset applies to the second flip-flop here. You'll need to complete these 2 values here in these 2 positions here, and then give me the actual data outputs. Okay, fine. Let's see how you do when we grade that result. Now let's continue. We will now look at our final subject, which is concerning looking at a counter. Now, a counter is also a register, a sequential logic circuit, which deals with the generation of multi-bit sequential code, such as 0, 1, 2, 3, 4, 5, or maybe something in reverse. If a counter can do more than that, it's called a multi-mode counter. Such as in a lab that you've taken, you had a multi-mode counter that had an input M, and M could stop the count or cause it to count forward. You can also have other modes such as up-down mode. We will also look at counters that are 2 examples today, a synchronous counter and something we will define as an asynchronous counter. We will also show you in an iClicker exercise how outputs provide frequency division. And so let's go ahead and get started. Let's begin first with the synchronous counter. A single mode synchronous counter is shown below. It consists of an array of JK flip-flops, and the data in this case is flowing from the right to the left. And it's all driven by a common clock line. So the clocks are entering in this case. Now we are going to use negative edge triggered clocks in this particular case. The flip-flops are configured to be either in the toggle mode, which I indicate with a T, or a no change and toggle mode for these remaining 2. Let's see how this works. By the way, as I'm bringing this up, you might want to ask, you did build a counter in the laboratory. It was just 2 flip-flops, actually. What is the meaning of all these things, and where is the read-only memory? Well, the read-only memory is how they build counters now, especially because they can be very long. It's 32 bits, 64 bits. But initially, when the counters were designed, they were built from gates, and it was efficient to do that. And we're showing that example here. So there's no read-only memory in this design. I am now going to show you some timing diagrams that are shown on the bottom here. I'm going to have them go vertically, and starting off here on the top, and then wiggling as they go down. The first flip-flop is configured to be in toggle mode. Every time there's a negative edge on the clock, because of the bubble here, we're going to have a toggle, a toggle, a toggle, a toggle, and a toggle. The result of this waveform is that it oscillates at 1/2 the frequency of the initial clock waveform. If I look at the second waveform, it also behaves in a similar manner, except there is now a no change operation that is brought in. And what happens in this particular case is that the length of time that it's down and up, and it goes up when you have a toggle, it goes back down when it has a toggle, that length of time is extended by a factor of 2 with respect to this. If I extend this idea to the other 2 waveforms, I will see this pattern such that the waveform frequencies go down by a factor of 2 on each successive stage. And that is called frequency division. So let's take a look at an example of this from the quiz, which is right over here. We'll again begin with example number 1, and I did mention in class that there will be a question like this. One of the four registers that I will be discussing today, and I've talked about 3 of them now, will appear in this position here. It'll either be a data latch register, a shift register, JK or D. It'll be a synchronous counter, which is this circuit here, or it could be the ripple counter that I'll be getting to here shortly. Be aware of that for the future exam. Now let's go down to the problem I like to examine, which is question number 4. The question says, which of the waveforms shown down here, and I'll give you a better diagram, is generated by the output QB of this counter? Now let's go take a look at a better version of this so you can see this. And here it is. So in this particular case, the clock waveform starts here and it goes across. Then there are 5 waveforms below that, some of which are showing the answers that we want to see, and some of them don't correspond to anything that we want to see. We'll begin by taking a look at what the first waveform from the first initial flip-flop will be. That would correspond to, in our diagram, to this picture here and this waveform here. All right, QA is going to have a waveform that's half the frequency or double the clock period of the clock. Now consider the 2 points on a clock, such as here and here. If I double that length, which of these waveforms correspond to that? I would propose that this waveform here goes up and down twice as long as the clock does over here. Let's call this period TA. So this would correspond to the output for Q sub A. But the question we have is, what is Q sub B? Q sub B will have 1/4 the frequency, or 4 times the period of the clock, such as shown over here. Looking at the waveforms, I can see that this entry here has that requirement. So therefore, this must be the clock period corresponding to QB. Therefore, the answer to this question is QB is therefore equal to QB4. Now it's your turn. Corresponding to writing an answer in the blue box, QB equal QB4 with no spaces, tell me what the waveform is associated with QC if you obey this relationship up here between the period of QC and 8 times the period of the clock. And then that will be the exercise that you do, and then you can also consider what QD is. Now let's return back to the notes. The last counter, the last register that we'll look at, is the ripple counter. The ripple counter is famous because it is the one that involves the least amount of exterior logic besides the 4 JK flip-flops. The architecture consists of, again, 4 JK flip-flops, but they're only configured in toggle mode. It is an asynchronous circuit because the clock is applied only to the first clock input. Subsequent stages receive their clocks from the Q output of the previous stage. Let's see how this thing works. First of all, the first stage is exactly the same as the first stage of the earlier circuit. Comparing this one with this one, they're identical. So therefore, I know how this one works. As I apply a clock pulse here on the negative edge triggering of this waveform, I will get a toggle. Toggle, 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 toggle. This causes a waveform to be frequency divided by a factor of 2, resulting in a clock waveform that is twice the period of the clock as we saw earlier. Now, Basically, the other waveforms obey something similar, but it's not quite the same. In other words, this is approximately twice the previous, and this is QD is approximately the waveform. This is QC. QC is approximately twice the waveform of QB. But there is a difference here. The difference is due to the fact that the clock is only being applied to the first stage, and the second stage has to wait for a change before it can change. Let's see where this manifests itself. Consider the numbers that this counter generates. 0, 0, 0, 0, 0, 1 in blue, 0, 1, 2, 3, 4, 5, and 6. Those are the six first numbers of the counter. However, because there's some delays here, the change in the flip-flops there are some differences in time between the change of one flip-flop to another. For example, when I change between the blue 1 and the blue 2, two flip-flops have to change. Well, because they're not changing simultaneously, the first flip-flop changes for a brief moment to be a 0, while the other two remain to be 0. Then, a very short period of time after that, that 0 then changes to a 1. So then I arrive to the final answer of 2, but I have to go through a green transient state in between the 1 and the 2. In a similar manner, between the counts of 3 and 4, the first flip-flop changes, then the second flip-flop changes, and then finally I arrive at 4, resulting in 2 transient states. Now, the reason that this is happening is because the changes are rippling through the various stages here. Something like in a football stadium, when you see a section stand up, and then the next section stands up, and then the next section stands up, and then, of course, they sit down. As opposed to everybody in the stadium standing up to sing the national anthem, or something like that. So this ripple effect is actually done in real-life situations. The other thing to observe is that the small transient states here are not observable to the human eye. So therefore, when you build this in the laboratory, you will, for example, you would never see it. But it would wreak havoc in a computer system because the computers do see this kind of problem where you have transient states. Okay, so now let's take a look at some examples. What I like to do now is, for your final iClicker exercise, let's look at 2 examples and then give you your iClicker exercise where I ask you to identify some transient states. Now, the 2 examples I'm going to cover are these 2, which turn out to be 2 problems from the quiz. Let's go turn to the quiz for a minute. The first one here that's dealing with this problem is question number 6, which asks, what are the transient states between the count of 3 and 4? We've already looked at that, but let's go ahead and do it again. And then we have a question number 8 as well. So the question is below this. Let's go ahead and do that. I've got it partially filled out already, it looks like. So here's the count of 3 for question number 6. We know that it goes to 4. How does it get from 3 to 4? Well, remember how it works in the football stadium. The first section changes. Say, in this particular case, they all sit down, so that we keep the other stages the same. Then the second stage sits down, and all the other stages stay the same. Now, obviously, in the football stadium, we actually stand up, but for the purposes of this, I guess we do have a stand-up here. In this particular case, the third stage stands up. So it's not quite the same as the football analogy. So we end up with 2 states, and the answer here is 2, and the answer here is 0. Let's find the answer on the quiz. If I can find it. I said it was 2 and 0. Let's press that. And so that says that that's correct and gives a little explanation of why that's working. The other question that we'd like to look at is similar to that, but it asks, instead of what those transient states are, it says how many are there. This does represent a little bit more difficult problem. Let's see how it's done. Here's question number 8. So we're going to go between here and here. So let's change the first flip-flop stage and keep the other ones the same. Change the second flip-flop stage, keep the other ones the same. Change the third one here. By the way, you keep on going until you hit the final number here. And then finally, we arrive at the number here. Now the question asked, is the number of transient states 2, 3, 4, or 5? 1, 2, 3, 4, and 5. The correct answer is 3. What do you think is the most common second most popular answer, which is incorrect? Well, given that you're writing it out in pencil without colors, you could see that it's easy to say that the answer is 5. But that includes the stable states of 3 and 4, actually, excuse me, of 7 and 8 that are not to be considered. So please do not put in the end caps here, just the ones in the middle. The answer is 3. Are you ready for your last iClicker question? This is the last one of the semester. So this is it. Relish it. I'm going to give you a slightly harder question. Between 11 and 12, I want you to change the states between 11 and 12, one by one, as you're doing here. The answer could be 2 states, it could be 3 states, it could be 4 states. And I would like you to do then is we will record the number, we will ask you to write in the contents inside this red box, okay? So should it be 2 rows, it would be 8 numbers. Should it be 3 rows, it'll be 12 numbers. Should it be 4 rows, it'll be 16 numbers, okay? So we're not asking, we're going to be copying more or less the problem number 6 here, idea, in question 11. Give me the actual numbers. Well, when this is graded, you'll have the final results. Well, that ends the last information that we have to give to you concerning registers and counters. This also ends the information I have for the entire course. So I wish you that you have a I hope that you had a good experience in this course. This is a boot camp course for electrical engineers and computer scientists. Should you be another major, then you took it as an optional course. This is the last presentation that I have, and you'll have either an exam or another meeting coming up. And I wish you well. Hope to see you one more time before the end of the course. Goodbye.